Hello and welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video I will talk to you about supervised regression in a nutshell. In the end, you should understand the basic concept of a regressor, you should understand the difference between L1 and L2 loss, and you should know the basic idea of the ordinary least squares estimator. You already know what a supervised machine learning task is. So here we talk specifically about the linear regression tasks or about regression tasks in general. So the linear regression task is to learn a linear combination of features for predicting the target variable. Let's start with an example here. As before with the example of cats and dogs, we have as input a labeled training data set, which consists of features, in this case rating, income and credit limit, and a target y, which is the credit balance in that case. So what the regressor does is it tries to learn the connection between the features and the target variable, and the output of the learning process is exactly the regressor. Okay, so the learner learns the regressor in the end. And the prediction time, we start with unlabeled data, which means we still have all the features of some new data points. Okay, if you look closely, you will see these are different from the data points above. And we do not know the target variable, which is the credit card balance in that case. So we use the regressor, we plug it in here and predict y hat, which is the credit card balance as predicted by the machine learning model, or by the regression model, or by the regressor. In this special case, or in this video, we will especially speak about linear combinations of features, which means that the model is this. So the credit balance is a linear combination of the three features plus an intercept term. So we have four parameters to estimate: theta 0, theta 1, theta 2, and theta 3. And now we'll see how we can do this. Before we talked about loss and risk and empirical risk minimization, and the goal of empirical risk minimization being that we find the best model, so the best element of the hypothesis space. And in the introduction, we talked about L2 loss. So L2 loss is just the squared residual. So now we have a new term here, which is the residual, that is the difference between the target and the predicted target, y minus f of x. And we can take these residuals and define different loss functions based on these residuals. On the left-hand side, we define the L1 loss. The L1 loss is just the absolute value of the residuals. You can see here a visualization of this. So on the x-axis we have y minus f of x, which are just exactly the residuals. And on the y-axis we have the different loss. We have the loss. So in this case, the loss is just this function, which is also called check function or a pinball function, which is just a function of absolute values. Yeah, 1 goes to 1, minus 1 goes to plus 1 as well, of course. So we have two examples here and there. So for x equals 1.04, the loss is 1.04, and for x equals minus 0.69, the loss is 0.69 plus 0.69. Okay, so that's fairly easy, I guess. On the right-hand side, we have the quadratic loss, or also called L2 loss, where we just square the residuals. This means, again, same type of plot. On the x-axis, just the residual. If we start here with 1.04 as well on the x-axis, then the L2 loss will be 1.09, which is the square of 1.04. And if we start here with minus 0.69 as well, then the loss will be the square of this, which is 0.47. And then we have this parabolic function. So these functions differ. Obviously, there are some advantages and disadvantages of the different approaches. So first advantage of the L1 loss on the left-hand side is that it's robust to outliers. So the loss does not grow that fast until infinity as compared to the L2 loss. But then again, the L2 loss is easier to optimize because it's differentiable everywhere. Okay, let's clean up a little bit here. So we can take the derivative here at each point, also at 0. And we cannot do this with the L1 loss. We can take the derivative everywhere but here. Okay, so it's not differentiable in 0. So the L2 loss is easier to optimize. As already said. And then the consequence of this is that the optimal parameters have to be computed numerically for the L1 loss. For the L2 loss, we have two options. We can compute the optimal parameters numerically as well as for the L1 loss, but there is an analytical solution, which is exactly the OLS solution, so the solution of the ordinary least squares estimator. Okay, let's have a further look into the differences of the L1 and L2 loss. And here we look at it from the angle of the model that we have learned with L1 and L2 loss. So important thing is that if we change L1 with L2 loss, we do not change the hypothesis space. In both cases, the hypothesis space is the space of linear functions. In each case, the optimal solution will be a linear function, in this case from limit to balance, but the exact parameters can vary between the two approaches. In the example, on the left-hand side with L1 loss, the estimated slope parameter is 0.14. On the right-hand side, for the L2 loss, the estimated slope parameter is 0.19, which means that in this case, the regression function is steeper for the L1 loss than for the L2 loss, is steeper than for the L1 loss. Okay, so the estimated, the best model differs if we vary the loss function. So perhaps you have seen this before, how we can interpret the parameters of the linear model, in this case the slope parameter. So we can say that if we have an estimated parameter of 0.14, then if the credit limit increases by 1, then the credit balance increases by 0.14 or 14 cents. Same thing for the L2 loss, of course. One very important thing is that this must not be misinterpreted as a causal effect from limit to balance. Okay, this does not mean that if a person changes its credit limit, that then the balance would do anything. So it's not an intervention, it's not an experiment. With this interpretation, we can just interpret what the model predicts. Okay, this means if we increase the credit limit by 1, then the model prediction will increase by 0.14. Okay, this is not to be confused with a causal effect. Well, I've already dropped the OLS estimator, that's the ordinary least squares estimator, which is the analytical solution for a linear model with L2 loss. So the nice thing about the L2 loss is, as said before, that it's differentiable in 0, or differentiable everywhere, but especially also in 0. So which means we can just compute the gradient, or set the derivation to 0 and solve this linear equation system. And then perhaps you've seen this before, and if not, doesn't matter too much here. So the solution, the analytical solution for the OLS estimator is this here. So the inverse of x transposed x multiplied with x transposed y. What's x and y? So here for the OLS estimator, we have a design matrix x. An important thing is that we add an intercept column here, which has the value of 1 for each observation. And this, why do we do this? So this corresponds to theta 0. Okay, this corresponds to theta 1, 2, and 3. And the first column corresponds to the intercept, so we need this one column for this formulation of the problem. Okay, and of course y is the target variable, the label vector. This is just as before. Okay, one final preview, let's say, on polynomial regression. So until here we said that all those models have to be linear, theta 0 plus theta 1 times a feature. But of course that's not that flexible, because we, well, can only fit linear functions then in the end. So what we can do is that we incorporate just the square feature limit and perhaps also the feature to the power of 3, and then take a linear combination of those new transformed features, which leads to a still linear model, linear in the parameters, but it's not longer linear in the features, which means that we have a parabolic function or a cubic function here. Of course, this is nice, because if the true data generating process is not linear, so then we want to be more flexible to really catch that true data generating process. So that's a pro in the favor of polynomial regression. So the disadvantage is that if we have too many of these terms here, so to the power of 3, to the power of 4, to the power of 5, so we can do this over and over and over, then at some point we can end up in overfitting. And of course there will be another videos on the details of overfitting, but in a nutshell, overfitting means that at some point we are too close to the data points of the training data without having a good generalization performance on new unseen test data. Okay, so the worst thing which in overfitting could happen is that we just interpolate all the data points. So if you have a very flexible function, let's say something like this, perhaps some sinusoidal or whatever function, so this just interpolates everything, but is of course, yeah, well, we don't really know how bad it is on test data. Perhaps this is the data generating process, the true data generating process, but well, I guess not. In that case, we end up in overfitting and don't generalize well. So we didn't really learn about the true data generating process, but just learned the data points by heart, and that's not what we want to achieve with supervised machine learning.